All right, wow, we're breezing through this pretty fast. That's awesome. Yeah. All this sticking. Any questions yet? Nothing? Everything's perfect? Okay. All right then. So multi-level queue. You might have multiple queues in running your processes, and you can, integrate foreground and background. You could think of this as maybe you'll have a priority scheduling, serve all the foreground before the background, aka you'll have a hierarchy of queues, and everything in the highest priority queue has to execute before any of the lower priority queues will execute. So usually that's what's done. Time slice, each queue gets a certain amount of CPU time. Maybe another way you could do it, you know, the highest queue will get 80%, next one 20, or maybe you'll divide it out from there. And it's very common for the foreground ones to be round robin, aka the ones you want to be running are very responsive, and the background ones are first come, first served because they need to execute, but if they don't complete immediately, it's going to be okay. Do you understand? You might have multiple, okay, great. Oh, here we go, perfect. Here's the picture. You want your system processes to be highest priority. Why? Why do you want the system processes to be highest priority?
Because it's an operating system.
It's an operating system. Oh, and it's greedy? And those in power tend to stay in power? Oh, I see. Yeah, it is kind of like communism. You got a point here. Think of it that way. Yeah. Usually the rest of these processes are waiting on some system process to complete. Because if it's waiting for I/O, I/O is a system process. So you want your system processes to complete ASAP. So everything else can actually all work. Interactive, aka your user's waiting for something to occur. You probably want those to run pretty quickly. Your batch processes, maybe just something in the background calculating, I don't know, the millionth character, pi out to a million characters or whatever. And then students, well, students. Multi-level feedback queue. So yeah, okay. Hopefully you can see if everything was a system process, nothing else would ever run. But you can still apply the aging technique as well as other feedback techniques in order to increase the priority. So yeah, whatever technique you use depends on your number of queues, scheduling algorithms, etc., etc. Basically, the operating system, it's an operating system. It can move processes from one queue level to another, depending on maybe the student process never gets a turn, so maybe we'll promote them to a batch process, at least for this one run, and then demote them back. Multi-level. Okay, 3 queues. Round robin with 8, round robin with 16, so, and first come, first serve. All right, good. Now we can actually do some problems. A new job enters queue 0, which is served round robin. When it gets CPU, the job receives 8 milliseconds. If it does not fill its 8 milliseconds, the job is moved to Q1 because it's completed up here. The Q1 job is again served. Round robin has 16. If it still does not complete, it's preempted and moved to Q2. Okay, if you're taking too long, you can also demote them. Hey, pictorially. Everyone okay with this? Usually people have a lot of problems with scheduling, okay? A lot of people have issues. They all seem to be getting it, which is awesome. Okay. So thread scheduling, obviously there's user level threads and kernel level threads. What's the difference? Ooh.
Safety.
Kernel level threads can do whatever they want.
All right. No. But good guess. You're thinking privileged versus unprivileged, or privileged versus user. Kernel threads are handled by the kernel, user threads are handled by the user. The kernel usually implements a user thread via either one kernel thread, multiple kernel threads, or
many.
Many, right. There's many, remember, it's many user threads to one, one-to-one user thread to one kernel thread, or one-to-many, one user thread and my many kernel threads. Okay, that doesn't make too much sense, but yeah, you could do it that way. AKA, you have a pool of kernel threads, and it could grow, and it stays that size, no matter how many user threads there are. All right, process contention scope. Let's see. I love how they just define it. Okay. Obviously, if you have a lot of threads, they're all going to be competing for resources, so you have to schedule those as well. But usually, inside of a kernel level thread, it's going to compete against other threads in the system, and a lot of operating systems, especially in Linux, treat threads and processes the same. So a thread is just thrown in with all the other processes on the scheduler. And pthreads actually allow you to change this. If you look up the pthread API, let me see if I can find the right one. I think it's man pthread set. What was it? Set adder? Nope. Should be an adder in here somewhere. Thread adder default. Pthread adder init. Okay. And then you should be able to initialize it later. Here we go. So you can set the affinity, set the schedule parameters, set the scope. Perfect. And pthread adder set scope. If you recall from pthread create, you can pass it a pthread attribute, and you can make it a system, basically on the system or on the process itself, aka user. So pthread, which is a standard API, POSIX thread, can be used to do this as well. Oh, here's an example. Set scope, scope system. You can actually set the scheduling policy as well. pthreads allows for first in, first out, real time, and other. So which one do you think first in, first out would be of the ones we've scheduled or used? Which ones have we talked about? Which ones have we talked about? Okay, I'll start you off. We have round robin. What else do we have?
Shortest job.
Shortest job first.
First come, first serve.
First come, first serve. One last one.
Priority.
Priority, yep. Okay. Which one do you think FIFO would be?
First come, first serve.
Yeah, it's probably first come, first serve. Although you don't have to be that way. You're really leaving it up to the operating system to decide. But chances are it's first come, first serve. Maybe shortest job first if the OS feels up to it. But it's probably first come, first serve. And then real time,
Priority.
it's going to be priority. Probably a mix between priority and round robin, but definitely a priority based one. And then other, basically like, I don't know, operating system, you figure it out. Probably shortest job first, or maybe set it a default priority that can be incremented. Okay. All right, so we have, here comes some more terms. You gotta keep these terms correct when looking at a scheduler. Someone ever goes online and finds a good tool for simulating the scheduling of a process, please tell me, because that would be awesome. That's not complicated. That's the issue. It needs to be simple. Everyone I've looked at is really, really complicated. But scheduling more complex with multiple CPUs are available, so you have load sharing. Actually, yeah, load sharing. So you want the CPUs to be sharing the load, not have one CPU take more than the other. Homogeneous processors, if you don't know already, means that all the processors are the same physically. For example, they're all x86 with same amount of L1 cache, L2 cache, same number of instructions implemented. A heterogeneous would be an example You have your, well, actually most machines are heterogeneous nowadays, because you would have your i7, for example, or i3 CPU, and then your graphics card is going to be running its own ISA, and that's a different processor. Although we don't schedule processes on there, you can use CUDA and other tools. So if you have multiple processors, in general they're some kind of homogeneous processor, they're usually pretty close to one another. Asymmetric just means only one process accesses system data structures, alleviate the need for sharing, while symmetric multiprocessing, each processor itself does scheduling, all processing common ready queue, and each have its own private queue or readiness. Which of these is better?
Asymmetric.
Why would you say asymmetric is better?
Because you don't get to share data.
Don't have to share data. All right. But from a performance standpoint, are you taking advantage of all the processors?
That depends.
That depends. Good answer. But in
Do you
general,
have all system level calls, or do you have user level calls?
you are doing an encoding or something. You might have a lot of processors. They're all sharing data, aren't they? Yes, sorry. I asked a rhetorical question. They are all sharing data. If they are sharing data, and you're having it such that only one process can work at the shared data at a time, then asymmetric is basically having your, I don't know, 12-core system act like one core, while symmetric can actually take advantage of the 12 cores. But what's the problem with the symmetric processing? So what I'm saying is the symmetric processing can take advantage of the extra cores, therefore improving performance of your overall system. But what's the problem with symmetric? Which is easier to code up?
Asymmetric.
Asymmetric's easier. You just have one giant lock and call it a day. The other one, we're going to have to figure something out in order to make them talk to one another. And we'll talk about synchronization in the next chapter. All right, process affinity. That erases so nicely. A process has affinity for the processor on which it's currently running. Why would that be the case?
Because then it doesn't have to send its memories to some other processor.
Right, if it's already loaded in the cache, if it goes to another processor, it's going to have to move all its memory from that cache or the main memory over to the new processor. So its affinity is the one it ran last. You have two of them called soft affinity and hard affinity. Soft affinity just means naturally, naturally the OS will have a tendency to always schedule your process on the same processor, but it's not guaranteed. It just normally does that. Hard affinity means you tell the processor or tell the operating system you will only schedule this process on the same processor at all time. So your hard affinity means you're straight out restricting it. Soft just means in general it happens because it's not required or enforced. Chris explained it very well. Here's a nice picture. If you have two cores, you have one process running over here with fast access to its memory, that should really say cache. All of a sudden you need to jump over here because you're changing process. That's a slow access because you need to move your memory around. So the affinity, you want to keep it on the same processor or the same core. This is called non-uniform memory access, aka NUMA, which you probably will see every once in a while. We talked about that. Yeah. All right. Recent trend to place multi-processor cores on a single chip. Wow. What year is this? Oh, 09. Okay. So as you can see, that has not gone away at all. All our chips are pretty much multi-core now. Yeah, so that's multi-core. It was technically talking about multi-processing, but the same thing really just happened with multi-core. Also, multiple threads per core is, they say it's, well, technically it's growing. Intel has always had it with hyper-threading where you can have two on one, and they really have just stuck with two threads on one core for the longest time. It wasn't until this year that AMD has released their version of hyper-threading to have two threads on one core. So I guess you could say it's growing, just not by much right now. I haven't figured out what's the best way to take advantage.
Is this the same threads as like a process thread?
Yes. The way this works is the The processor reports to the operating system, I am, let's say it's a single core with hyperthreading, then that processor reports, I'm actually 2 cores. And then the operating system would, put these instructions on this core, put these instructions on that core. And then the OS, the hardware would then know which thread is which. But none of that thread information is stored on the hardware. The operating system is telling the processor which, put this on this thread, put this on that core. Actually, put it on this core, put it on that core. So really what hyperthreading is doing is reporting more cores than are actually in existence, and then in the hardware taking advantage of which core should be executing on the actual core, if that makes any sense.
It's kind of doing round robin of processes.
Well, remember when we had fine-grained multi-threading, coarse-grained, and then symmetric multi-threading, or simultaneous multi-threading, I mean? That's what it's doing. It just reports itself as more than one core or processor. Let's see, thread. Just to show you that a lot of the time with a thread, it's doing computation and then a memory, computation, memory. Very common. And that's it? Okay, great. We're only going to look at the Linux scheduling, unless, Matt, do you really want to look at the Solaris scheduler?
Mm-hmm.
I think so.
I don't like the sun.
You don't like the sun? It burns? Yeah. Any objections? Good. All right, Linux scheduler, constant O of 1 scheduling time. That's what I was talking about earlier. All the computation to be O of 1, so it could be fast. We really have 2 priority ranges. So it's the overall scheduler is a priority scheduler. You have time sharing and real time. The real time is from 0 to 99, and nice value is from 100 to 140. Hey, figure 515. Are they going to give me that? Sure. So highest priority, 0, and it gets a time quantum of 200 milliseconds. So its time quantum is actually pretty high if your priority is 0. On the other hand, if you're a very nice process, you have the lowest priority and your time quantum is only 10. So it's kind of it's a combination of priority and your time quantums with round robin. Did you have a question? It has the active array, aka what needs to execute next, and the expired array, what is already executed until it's ready for the next jiffy or time section to start executing. So obviously 0 goes first, and then we put in the expired array, and then move on down. This gets rid of any starvation, because since you have 2 arrays, it has to go through the active array first and then move to expired array. And new process, if I recall correctly, gets added to the expired array. So that next time it flips over, it can start executing, if I remember that correctly. Right, you want your algorithm to be deterministic. We're talking about queuings and your implementation. Great. I don't know the point of this slide. All right, if I was able to find a simulator, this would make a lot more sense, because then we could actually have our list of processes, get our simulation up and running, plug in our simulation that we want, and then give us some performance statistics coming out. Fortunately, we're not going to have it for this class. It's what you get for, I guess, being the first time. And that's it.
Any first time?
This is the first time I've taught operating systems.
Used to be Underwood? Used to be Underwood?
Yes. Yep. But that's okay. You get other problems, like I assign you a problem that we never covered, or that the book's a liar. It's a different set of issues, right? Yeah. Any questions about Chapter 5? This is an important one, so make sure you do understand scheduling. You will see it on both your midterm and your final.
And quite possibly your senior exam.
And quite possibly your senior exam.
I won't see it.
Crack me up. All right, no other questions?